So this is section 1.4 and it's about Euler's method and numerical solutions to an initial value problem, and it was named after Leonard Euler, and he was a very prolific mathematician, lived in the 1700s from Switzerland, and he's one of these that is responsible for a lot of the notations we use. The f of whatever, like f of x, came from him. The I for the imaginary unit came from him, and our base E came from him for our exponential function. Anyway, the idea behind his method is if you have a differential equation, a first order one, you have a function of t and y, and so if you have a point t and y, you can determine the slope at that point, and then you could follow a line to linear approximate the function for a certain interval and then kind of repeatedly do that. So kind of as a visual, if this was the function, the solution to the differential equation, you know the slope at any given point. If you're given a point, you can put it in for the t and y and find the slope there. And so you would divide up the time interval into so many increments, and then you have an initial value, because this is an initial value problem. So you start at your initial value, you compute the slope of the tangent line to the curve there, and then you actually follow that slope until you get to the end of the first interval. So you'd follow that slope. At that point, whatever you get for your approximated t and y there, you can see it misses the curve because it's below it, but we don't have very fine increments here. You would actually put that new t and y in for the slope, find the slope of a tangent to the curve at that point, and follow the tangent line to the next time interval. So at that point you'd follow here, and then similar thing, you would have an approximation for the curve, a t and y, at that time point, and then you would compute the slope using that point, and you would follow the tangent to the next one, get a new point, and so forth one more time. Now you can see that this isn't very accurate because you're linearizing a curve, but we got the basic shape of the curve, and of course then what are we going to want to do? Well, we're going to want to make more intervals, shorter times where we follow, so that we can be more accurate. And if we did that, we'd have to compute it more times. But you can see at that point, if we computed it more times, that we did a better job following the curve. And it's still not great, but this would lend itself very well to using a computer and dividing it into even smaller increments and just programming in that slope. That wouldn't be hard to do, and just do iterations, taking what it gets out and then putting it in, finding the linear approximation there, and continuing like that to become more and more accurate. So the idea behind it is we have a first order differential equation that, so the derivative equals some function of t and y, and we have some initial value t naught and y naught. Now if you want to figure out the equation of a tangent line to the curve at the initial value, you would use our point slope formula. Y minus the y from the point equals the slope, and remember the function of t and y at that point is the slope at that point, and then times the difference between the t's, so t minus t naught. So this would give us the equation of the line, and then we could follow that line to get a next point. Now what we're going to want to do then, when we get that out, we're going to find a new point which will be t1 y1. So our y is going to be y1 and our t is going to be t1 here. So we could solve this for the y1, and we would have y1 equals the y value from the original point plus our difference between our t's, t1 minus t0 or t minus t0, is always going to be the same. We're going to do even spaced intervals, so we're just going to call that h. So you can see right here our h is just replacing our t1 minus t naught here, and then we have the function at t naught and y naught. So this piece is our slope. Now once we get that new y naught, we had our t naught from our interval, and then we're going to repeat this process, and so we're going to find y2 by using y1 plus that difference between the t's, that's our h, and then the function at t1, y1. And we're going to continue like this to approximate the curve, and so y3 would be y2 plus this, and so forth. So if we want a generalized pattern, we see that it's going to be y sub n is going to be the y from before plus our little width of our intervals for t. That's what h is. It looks like the parenthesis got in the wrong place right here. But then our slope, which is our function at t n minus 1 and y n minus 1. So you can see that I could program a computer pretty easily to do that, and that's exactly what we're going to do. I'm recommending you do it in Excel, and that's what I'm going to show you today. But you could use some other computer program if you're familiar with it and want to use that as well. All right, so just a few things. This is Euler's method. Just a few things first about it. There's going to be an error, obviously. We saw that we missed the curve. The shorter time intervals we made, the better it did, but there is going to be an error. And there's actually two types of errors. And the first would be a round-off error because you're computing the new estimate for y, and you're not going to carry it out to an infinite number of decimal places. You're going to choose to round it to 1 decimal place or 2 or 3. So there's going to be a rounding error, and every time you compute it, you need to make a rounding error, and so those can compile. So that's the first type. The second type of error is what we call the discretization error, and it's the error that results from the process itself. You're using a linear approximation and not following the curve. And so the combination of those two errors would be your total error. And it's not always, there's no rule of thumb that says round to this many decimal places or make the intervals this small. The errors kind of work in conjunction with each other, and it's typically sort of a combination of the two that gives you the best. And here's a graphic that kind of shows you that. So you've got the round-off error, and then you've got the discretization error, and the total error then falls somewhere between. And the book says determining critical step size is more an art than a science. So we're not going to stress a lot about it at this point. There's an entire course on numerical analysis that would get into this more. Right now we're just going to do some basic differential equations, and it won't be an issue. Now, after Euler came up with his method, then they looked at it and modified it to improve even more. And so there's two more methods we're just going to look at. We're going to look at a modified Euler method, it's called, and this one is trying to kind of look ahead at a value so you can do a better job if it was really going to miss the curve. We are going to do this one in the lab as well. So this is the formula to get the next y value, the y sub n plus 1. You take the y value, but then you're going to average two different points. So that's why the 1/2, because there's going to be 2 points. We still have the h, which is our t width, and then instead of just taking the function at t sub n, y sub n, you're going to take the function at t sub n, y sub n, and you're going to add that to the next t's value, and then what you would predict for that next value, and that's shown down there below, the y star, and you're going to add those two values together and divide them by 2, so you're taking the average, and that helps so that if the curve changed drastically for the next time interval, that'll help take that into account. Now, the last one is called the Runge-Kutta method, and it was by a couple of German mathematicians, and they said, well, if you were going to average, then let's maybe try and get some more points, and we'll kind of weight them differently. And so a lot of computers, that when they started programming computers to numerically solve differential equations, which means they weren't, quote, solving them, they were getting numerical approximations of them. But anyway, a lot of those use this Runge-Kutta method. I think they have something even a little more sophisticated now in general, but this was a commonly used for a long time method. We're not going to do computing ones here because it's pretty involved, but just to give you a general sense and be aware that it's out there. You start with your value and you start with your little width, but for the function of t and y, you're going to compute 4 different k's, and you're going to weight the middle two heavier than the n2, because the n2s start at your function of t sub n, y sub n, and one after that, and then these are doing some values in between. And anyway, they would program this computer to do that. Now we want to see an example, and so I'm going to use this example, and I'm going to use a spreadsheet, and I'm going to show you how I'm going to build this spreadsheet so that it computes this example. But I'm not going to do that in this video. I'm going to open a new video where I go into the spreadsheet, but you may want to write this info down. We're going to do the first order differential equation where y prime equals 2t plus 1. This is going to be very simple to solve. We could have solved this one with the first thing we know, which is just direct integration, and we can integrate both sides, and we're in fact going to solve it because that's part C. We're going to compare it to the Euler approximations with a couple different step sizes. So we got our 2t plus 1, and we got our initial value y of 0 equals 1. So we're going to use the Euler method to approximate solutions with 10 approximations of step size 0.5. Then we're going to repeat that process, but we're going to make the step size 0.1. We could actually expand and do more steps because we made them smaller, and so 10 steps is only going to get us to 1, where we may want to do some more steps when we do B. Then we're going to compute the solution, and we're going to compare those. So that's what we're going to do in the lab in general. This is just an example so you can see one, and then you'll want to get your lab and follow the directions for what things it asks you to do for the lab.